So first of all, it's my great pleasure to be here in this conference celebrating 60th birthday of Professor Jean-Pierre Demailly. I'd like to thank the organizers for their kind invitation. So I met Jean-Pierre, I believe, for the first time when I was giving a lecture at the Séminaire Le Long-Sco de Lobo. And this was in the summer of 1982. And actually, the Professor Skoda then indicated this was a bright student of his. And from all accounts, this is someone going to be a rising star. And in fact, the trajectory amply proves that. So I was aware of your work. Actually, I think this was as a graduate student, you were working also sort of on the side on the problem about the Serre problem. And Skoda was giving a counterexample for two-dimensional, higher dimensional fibers with Cn. And then those were functions of exponential growth. And then Jean-Pierre gave the then counterexamples of polynomial growth. So I remember that vividly because I was working on a one-dimensional case, knowing that two-dimension is actually a force. This has certainly spared me a lot of time trying to, I would otherwise have thought that it's worth trying, at least for the case of polynomial growth. Yeah, so, and then Jean-Pierre was very much interested on the interface between the, shall I say, complex analytic theory and algebraic theory. The borderline between complex geometry, complex differential geometry and algebraic geometry is very, difficult to delineate. And also, this is an interface in which I'm very much interested in. So today, what I'm going to talk about is in that direction, although somewhat different. I would be dealing with the differential geometric theory without metrics, and but somehow, sometimes also, of course, metrics help. But this is the backdrop. So I'm talking about theory about Uniruled projective manifolds. Very often I would be specializing to the case where a Picard of X. This is not always necessary. So in general, one would be interested in the projective manifold X filled up by lines or filled up by rational curves. So in case any 2 points can be joined, then this would be said to be rationally saturated. And when you say that this is uniruled, it means that there exists some free rational curve, and which can be then free, meaning that you take for simplicity, assume that this is a smooth curve. So this is going to be a direct sum of OAI, once the dimension of X, where AI can use 0. So this is a free rational curve. Of course, in general, one should work with F from P1 into X, so it's possible that this curve is immersed or has self-intersections. Okay, so the very beginning of this was a big program that I developed starting in the middle of the 1990s on what one could call VMRT theory, or the geometry of VMRTs. What it means is the following. Now, you look at what one calls minimal rational curves. There are different definitions of this. Let me just take the practical definition. I take a polarization. So in general, this could be of high Picard numbers. And you just look at curves C such that, look at maps FP1 into X, and which are free rational curves, such that the degree of F pullback the degree of L restricted to X is actually the minimal among free rational curves. In general, you take the pullback by the map. Okay, so then one can define for such varieties the universal family. So using HOM, and you have the following picture. So this is the manifold X, and on each fiber you have UX, and then here you have a K. This is a moduli space of minimal rational curves belonging to a certain universal family, and you have therefore a certain P1 bundle, generically a P1 bundle. So there could be places where you have more than one component, and then you have here, this is the evaluation map, and this is the universal family. So okay, there are in fact two pictures which are sometimes isomorphic, but let me, you can just take this picture and change this to another name, which is C. What it means is the following. Now, if you take a point and you look at the rational curves passing through it, and then you can also look at their lifting to the tangent bundle, and therefore you get what is called a tangent map. So the tangent map, tau, at the point x, is a rational map which sends ux into ptxx. And for x, a general point, we will be looking at cx by definition equal to tau x ux, the Characterization closure of tau x ux. Well, not Characterization, well, topological closure, actually. So, as it turns out, by work of Huang and myself, we proved that this is going to be a birational map at generic point. Then there was work of Kabakis, which, these are we proved that it's a birational map at general point, and then Kabakis proves that it is actually smooth. So at a general point, actually, all curves, minimal rational curve passing through it are immersed. And then finally, we came to the conclusion that tau is a birational finite morphism. In this lecture, I'm more interested in sort of classical manifolds. And if you take the case of this Uniruled projective manifolds, for instance, you can take a hypersurface D inside Pn, D of sufficiently small degree. Then you have a final hypersurface, final hypersurface Uniruled by lines. So as long as the Chern number is bigger than or equal to 2 is Uniruled by lines. Then actually, in this case, the tau x ux is actually a biholomorphism with the cxx, and this is called the variety of minimal rational curve in general, of rational tangents in general. Okay. Now, so this is a universal picture. So I would be looking at, let's say, more in the classical situation, if actually a P1 vibration. And then, so this picture is isomorphic to the picture replacing ux by cx. And we were studying this space, or these three spaces equipped with certain full distributions. So there's a natural distribution, which one can define. So there's a natural distribution one can define on K as follows. Now, for a generic minimal rational curve, you have the following splitting. And so the tangent space to this particular curve as an element of K is actually given by
sections. But then there's a certain subset consisting of those sections which come from the positive part. So let me call this the positive part. So that's gamma C of the positive part. And this defines a certain vector subspace at each point, and therefore a distribution throughout K. And we call this distribution D. So D defines its distribution. And there's another way of defining distribution over here, and it's the following. If you take a rational curve here, so you have the splitting type, O2 plus O1P plus O. And then let me define P of X just as the positive part. So as being the positive part in the Grundy splitting. And then I can define a distribution defined over here, which I would denote by P. And so P at a point, let's say alpha. So I'm using the C picture. So if I take this with the tangent direction alpha, and here this the point alpha, then the P alpha is going to be, by definition, d mu inverse of Px. And it turns out that this is related to the distribution on K, and this is equal to d rho inverse of the distribution D. From this description, it is quite immediate that the tautological foliation actually is in the Cauchy characteristic of the distribution P. So I can define a foliation. I call this F. So F P is actually inside P because it's actually in the kernel. So it's just the inverse of 0. So, okay.
The tangent bundle of K and C shouldn't be the section with the normal bundle.
Normal bundles, thank you. Yeah. Yeah. So, okay. Okay. So now this is the Cauchy characteristic. The question is whether this is whether the Cauchy characteristic is the whole part of it. Well, actually one can do some computation, and it turns out that this would be the case, assuming that a certain condition on second fundamental form is satisfied. So this is the sort of a lemma. It says that, so if the Gauss map of Cx inside PTXX is injective at a general point, then the Cauchy characteristic of P is exactly equal to F. Okay. I should have started with this front board, but okay. I think you can keep this these pictures in mind. That would be. Okay, so this lemma actually was used in the proof of the birationality of the tangent map. But A little later, you had the Gacon-Fubini extension theorem. But let me give a prototype of this, which is of importance. So this is a theorem of OCI. It's 1970. It's easier to draw this. So suppose I take S, which is a Hermitian symmetric space, irreducible, and assume that this is not Pn. And suppose I have a map from two open sets, you connect open sets, you have a map F such that F respects the S structure. By this, as an example, if you take, for instance, you take a Grassmannian GPQ, then the tangent bundle of the Grassmannian and a P then equal to 2. You have tensor product decomposition of the tangent bundle. By saying that F respects this Grassmann structure, it means that it respects the tensor product decomposition. So in general, one can formulate this in terms of reduction of the frame bundle from the general linear group to a reductive, a certain specific reductive Lie group, which is a complexification of the isotropy. Now, so on this symmetric space, if you have such a map, then OCI theorem says that. So OCI theorem says that there exists F belonging to automorphism of S such that F restrict to U to be small f. Okay. Now it turns out that respecting the S structure is the same as saying the following. You take df, C is actually equal to C. So that's the variety of minimal-rational tangent. For instance, in case of the hyperquadric, the minimal-rational curves are the null geodesics. So it respects the null cone, so to speak. In case of Grassmannian, what you have, so Cx of GPQ is actually isomorphic to P minus 1 cross P, Q minus 1 embedded inside P Q minus 1. Okay. So then this condition can be reformulated as VMRT preserving. So this is the so Gacon-Fubini extension theorem. This is due to Huang myself. It says that suppose I also take this picture. This X of Picard number 1. So and Uniruled by minimal rational curve, so endowed with the minimal rational component K. And suppose I have a map exactly like this with the property that dfc of x restricted to U actually is equal to Cx restricted to V. Then this implies that there exists F. Well, actually, in this case, it doesn't have to be one single manifold. It could be on two different manifolds. But let's just put it this way. So that such that, so this is a biolomorphism such that capital F restrict to U is the same as small f. Okay. And the starting point and the crucial point of this is the preservation of the tautological foliation. Think about a case like the Grassmannian, this classical manifolds. You can make use of sort of projective geometry. There's a dual manifold. The manifold, in this case, the duality means actually taking the moduli space of lines, the final variety of the manifold. So then if I can prove that lines are mapped into lines, I would induce a certain map on the space of lines. And this map will be defined on a pseudo-concave or open subset, and then you have extension to the interior. After doing this, that is on map extends, then the initial map also extends by taking intersections. So this is, you get a birational map, and a birational map in this case would have to be a biolomorphism if it respects the VMRTs. Okay, so this is basically what is done. And so, so how was this proved? This was proved by simply this. You take the foliation F, and then you have another foliation. But then this also satisfies, because P is invariant under F. P is actually a distribution defined uniquely by the VMRTs. And therefore, it's actually inside. But this is the same as P, but on different open sets. Okay, so it implies that therefore F is preserved under F, and then the rest is well, techniques of analytic continuation. So you get some moduli map from open sets of another X prime, and then you do analytic continuation. So there's some technical, well, techniques from sort of the classical surface complex variable domains of holomorphism and so on. But in this the classical situation, you have actually a dual space which is understood. Okay. Okay. Now, okay. So this is the setup for the geometric structures. I would call, for simplicity, so you have this manifold X, xk. So this is a mini-rational component, but I would be looking at more xc, so equipped with the VMRTs. And so this is, in some sense, a certain ambient manifold. Towards 2010, I was thinking about sort of developing a certain extrinsic geometry for VMRT spaces, so to speak. So XC, this is taken as a geometric object, and one would be looking at subsets of it. And what I have in mind was studying Uniruled projective subvarieties. Now, but even if of course, everybody knows that for deformation theory, you have to be working with smooth objects. So once you have singularity, things are very much different. But nonetheless, if you want to study the, so to speak, extrinsic geometry, it's meaningless to impose smoothness on the subset. And actually, as I said, this is a differential geometric theory, and I was trying to work with the complex topology. So I was looking, therefore, on open subsets in the complex topology of the manifold X. So then, so at the back of my mind, I was trying to develop something one could call sub-VMRT structure. So I did some work in 2008 with the Grassmannian, and then in the joint work, this is 2010, we developed what one could call the non-equidimensional Garfin-Fubini. So what we have in mind is the following. Suppose you take, instead of just one VMRT, so this is a CXX, and this is a CXS, or CXZ. So look at a model. So look at a model. So for instance, you can take this to be X. This is a Grassmannian, GPQ, and this is P prime, Q prime. And let me make the assumption that P, these are bigger than equal to 2. So this is a certain distinguished linear section. So then I was looking at, special subvarieties. So they are, in some sense, the replacement of geodesics, but I don't use metrics. Okay. So the question is to characterize such sets in different ways. It turns out that this type of problem was actually studied in a different context, in the context of so-called Schur rigidity. And there were early works by Waters and Brian, and then Hong's work was, I think, 06, in which they were looking at the following question. Suppose you have a zycle Z inside X. So you ask whether, and you have Y, such that the cohomology class is equal to Z, the question is, does it imply that y is equal to z up to some global automorphism? And you could go further. Instead of looking at this, you look at some variety. So sure, rigidity actually one look at y equal to r z. Does it imply that actually y is equal to g1 z plus grz? So this is the question of sure rigidity. And this was answered in the positive for certain Grassmannians and some other classical manifolds by Waters and Bryan. And then Hong settled the question in case of Hermitian symmetric spaces. So this was therefore classically known. So how to characterize this as a cycle. But I was looking at this, and then in the case of Grassmannian from a different point of view. So essentially, in the work with Hong in 2010, we developed some general machinery to study the following question. So the non-equidimensional Garton-Fubini. So we define a certain relative second fundamental form condition which guarantees that actually when you have a map respecting VMRTs, then this map extends rationally. And I should say that in general, this does not hold true. A simple example is that if you look at the hyperquadratic, this given by the twisted quadratic form, and you restrict to any submanifold, you still have the twisted quadratic form, and generically this would be non-degenerate. So something emitting such a substructure on an open set is rather a generic condition. But how about in the case of Grassmannian? In case of Grassmannian, you would be looking at a picture like this. It is p minus 1 prime cross p q prime minus 1 sitting inside p. These are the VMRTs. And if you count the dimension, this is you are intersecting this guy, u prime. And generically, you expect a dimension much smaller than this. So this is in the situation where you have excessive intersection. So this is the key, the conceptual point. So you're looking at linear structure defined by certain submanifolds. At the very beginning, we were doing the non-equidimensional Garton-Fubini, and so we were still looking at the context of maps. So F would be something like this. So from a certain U, a certain connected open set in Z, and you have a map F from U into X, and this is VMRT respecting. It has a certain technical meaning. It means that dF, if you look at, this means affinization. I go to linear space instead of projective space. Cx of Z is actually equal to dF T x of Z intersection C Fx. Maybe notation X is not very good. I use Z. So this is VMRT respecting. And then we found a certain relative condition, which in the case when they are of the same dimension reduces to the condition that the Gauss map is generically injective. So we were looking at the kernel of the second fundamental form at a point. So alpha is a point which is in Cz of Z, second fundamental form. And you're looking at here dF of so this is regarded as this, and the condition is that now I'm looking at affinization, then the condition is C alpha. You can objectivize, it means that there's no kernel. So what it means is that I am looking at a pair. So instead of a single VMRT, I'm looking at a pair of VMRTs. And you take a point here, and you're still looking at the second fundamental form of this ambient VMRT inside this projective space, so PTXX. And you look at its second fundamental form. You restrict one variable to the subset, and you look at the kernel. And the condition is that the kernel should still be C alpha. In that case, we would say that it is non-degenerate for mappings. And the theorem, I should say proposition. So VMRT respecting plus pick up condition on Z plus non-degeneracy for mappings then implies that F extends to a rational map F from Z. Okay. The way I write U is a subset of Z, so then from Z into X. So this type of theorem then used for characterization of certain subcycles. And back to this question about characterizing. So lately, I was developing, together with my student, a certain theory for substructures. So let me formulate this. So we can look at the situation in more classical case. So always keep in mind this situation. Have this model for sub-Grassmannian inside. And for simplicity, let me assume again that the rank is at least equal to 2. Okay, so I have, this is a model of a pair. Okay, so I have a certain final manifold Picard number 1. And I have on this submanifold a certain connected complex submanifold, and one defines the following. We define. So X is a point on S. This might not be the best notation, but I don't want to have very clumsy notation. This is equal to, by definition, just Tx of S intersection Cx of the ambient. So we were trying to develop a theory for submanifolds. Okay. So I can projectivize. So this, affinize it. So work with linear spaces. Or equivalently, it means that if you work, you can also take this as Pt inside. Now, okay. Now, I said this is not very good notation because usually when we use Cx, this means the VMRT. But I don't have a VMRT. I'm just taking intersection. So for instance, if I start with X being hyperquadratic, as I explained, well, you can always take submanifold and look at this. And you have some non-empty set of tangent vectors. And they are not very interesting, because a generic manifold, you can still have lots of such vectors. So, but the question is, when can I find Z algebraic is such that, so of dimension equal to dimension of S is such that S lies inside Z. So you want to look at a sort of algebraic completion. So a crucial question in this context is actually passing from the complex analytic topology to the algebraic situation. So then for this purpose, we introduce a variation of the second fundamental form condition. Which goes as follows. Okay, before I go on, maybe I should first say something about the application of the non-equidimensional Garton-Fubini. This is a general theorem about extension of the map. But in the special case where you have a pair, and so you have x0, where this is G mod P, and this is G0 mod P0. And for simplicity, assuming that this is sort of nonlinear, and this is a Picard number 1. So this is a maximal parabolic. Then Hong and myself prove that actually so in general you have f, let's say in the situation z going into x, then this f of z is actually equal to g of x0. So there's a general theorem about the Uniruled projective varieties, but in the special case coming from a pair of flag manifolds of Picard number, or of G mod P of Picard number 1, then actually we can also say that this is going to be a transform of the standard model. Okay, so this is sort of a rigidity theorem. And this is under the assumption that this is defined by Dinkin diagram. So you just take the Dinkin diagram, and this is defined. For instance, you look at something like this, and it's defined by this node, then this would be a subdiagram. So in this situation, we can prove a form of rigidity theorem. And then in 2013, we were studying together with Hong again. So we prove sort of Schubert rigidity. That is the Schur rigidity problem with R being equal to 1. And in principle, this should be generalized to a case where R is bigger than 1. This is ongoing. And where one proves that actually when you take a pair like this, then a holomorphic or a cycle whose class is the same as the cycle x0 is actually going to be a translate of x0 by a certain automorphism. Okay. So this goes beyond the situation of Hermitian symmetric spaces. For Hermitian symmetric spaces, there's a method using, actually this is differential geometry. You look at the cycle in some dual forms, and this form turns out to have a certain sign, and then you can work on that. And when you have a certain cycle whose class is given by the model, then actually one proves that the tangent spaces of the cycle has special form, being isomorphic to that of the model. So this is very much like the case of, well, you can say that this is a precursor to subvarieties theory. So developed also Walters and Bryan and then Hong. And then lately, actually, the Schubert rigidity or the Schur rigidity problem was completely settled by Koblitz and Tay, and they make use of Lie algebraic homology theory, as was already in the very beginning, and this is very algebraic. Again, this was for the case of Hermitian symmetric space. So you may say that one of the motivation, and this is one of the motivations, was to develop a substructure theory applicable to rational homogeneous spaces, which are not necessarily symmetric, and also in particular to singular varieties. So this actually settles also the singular variety situation. But yeah, okay. So then we define a certain form of a variation of the second fundamental form condition. So let me just write that out. So second fundamental form was as I explained, but then I define where nu alpha is the following. So the picture is that I have manifold X, a submanifold S, and then I define CXS. So you take a quotient. This is a T alpha tilde. And then you have to add something to it. And this is adding dx intersection submanifold, where dx is the span of Cx x. Okay. So you quotient out a certain subspace. Well, in the absence of map, so the basis of the proof of the non-equidimensional Cartan-Fubini is to look at the complex hashing of the map. So there's symmetry in the complex hashing of the map. So in case of the complex hashing, when absence of a map, one would then look at second fundamental forms in space. In that case, when you take vector fields, you can. So I have some manifold equipped with a pair of VMRTs, and then on this manifold X, and I have a submanifold S, and then I can sort of extend vector fields with respect the sub-VMRT along S, and which respects the ambient VMRT on the neighborhood U of the manifold, and then one make use of them to compute Lie brackets and so on. And then it turns out that one has to modify the second fundamental form by this projection, and then one can define a certain non-degenerate condition. This might be called non-degeneracy for substructures by the following condition. So we say that this is the case if kernel, so if and only if kernel of tau alpha. So again, this is df. Yeah. There's no map here, so. This is going to be exactly. Now, the two conditions are not equivalent, and actually neither one implies the other. But in the special case where you have this pair, a model on x0, x, where this is defined by Subdingen diagram, by means of root space decomposition, one checks that the two conditions are equivalent, at least in the case when you have the nonlinear subspace. And therefore, the checking that has been done directly about root systems for the non-degeneracy for mappings also applies to substructures. And the conclusion is that, for instance, in the case of Grassmannian, some subspace admitting this Grassmannian substructure has to be, in some sense, well, satisfy this condition. I didn't say what this implies. This then implies that this S is rationally saturated. Rationally saturated means the following thing. It means that if I take a line that is tangent to S, the line has to stay inside S. And the philosophy, like rational connectivity, is to say the following. I want to reconstruct this subspace. And this subspace can be reconstructed if I know that lines tangent to it are already on it, and then you can connect points by point by taking chains of such minimal rational curves or such lines. And this can indeed be done under some conditions. This is one of the condition of non-degeneracy for substructures. There's one additional condition. And this additional condition can be understood in the, well, geometrically, I would say, in a few minutes, but in 1 minute. Okay, so there's also something called a condition. This is, means tangency. And the condition is the following. You take T alpha. This is defined by intersection. This is going to be this condition is simply saying that the intersection of the VMRT with the tangent subspace of the submanifold is actually reduced. And this is not always satisfied. And when this condition T is satisfied, so what one could prove is that condition T plus non-degeneracy, so this is joint work with myself, then this implies that this S can be complete, well, it's rationally saturated. If one imposes one more condition, well, actually two more conditions, if furthermore VMRT mean rational curves are lines, that is, they're homologically the generator of H2, and D equal to the span of CXS is bracket generating. That is, by taking successively brackets, you can generate the whole tangent space of S. Then implies that S can be embedded more or less as an open subset of this algebraic. So this is an algebraic completion theorem. In terms of more classical problem about rigidity, actually we prove that the pairs of Dinkin subdiagrams, at least for the nonlinear ones, so they are rigid in some sense. This rigidity says that the submanifold is dictated by the isomorphism classes of the tangent subspaces. Okay. Now, finally, let me say something about the meaning of the sub-VMRT structure. I had at the very beginning thought about this not just as a theory for the Uniruled projective manifolds, but it should have implications for Kähler geometry. Well, of course, for classical manifolds. And here is a theorem that can be proven by this method. So this is work that I do with my graduate student Yang. It says the following. Okay, so let me first say something. If you take omega, and this is an irreducible boundless symmetric domain, so you have the Harris-Chandra realization. You take a point in the boundary. So a few years ago, I constructed an example of an isometric embedding of the ball. Isometric embedding, so suppose VMRT is of dimension P, then I have a P plus 1 dimensional isometric embedding of the ball. And simply by taking one point and shooting off all the lines passing through this point, and this point should belong to the regular part of the boundary of omega. And this has dimension P plus 1. And if you want really an isometric embedding, then this is the maximal dimension that one can reach. And then the question is the uniqueness question about such isometric embeddings. It turns out that, well, this fails in the case of duals of hyperquadrics. And Chen and myself have a complete classification of the isometric embeddings in the case of duals, so type 4 domains. This is completely classified. And then there were later on works of, I think, Ming Xiao and Yuan, and also the work of Kai Zhang. So generalizing in different directions. But then the uniqueness we were able to do in the rank 2 case. So suppose X, suppose you have Z inside omega, and isometric embedding of the ball of dimension p plus 1, and omega is of rank 2, and also that this is not isomorphic to type 4 domain, then implies that S is isomorphic to the model up to the model is drawn here. And the relation to subVM multistructure is the following. By an application of what is behind what is called the Hirzebruch proportionality principle. So Hirzebruch proportionality principle comes from the duality in curvature when you have a pair. So you have Borel embedding, you have a pair. Making use of that principle, or the underlying reason for it, and computing Gauss maps, we were able to identify the isomorphism type of the tangent subspaces to this S. And then from there, one makes use of this chain of rational curve argument to recover the manifold. So this could be done for the rank 2 symmetric spaces, but also in certain rank 3 cases. For instance, we could do the E7. E7, this is a rank 3 situation. And then Yang, in his thesis, did also the rank 3 Rachmaninian. For the other cases, there are technical difficulties, and we're still looking at it. Okay, let me stop here.